So, I think maybe the kind of the overall temporal theme of the day, right, is going from some of the earlier history of the School of Computing to the more recent history of the School of Computing. But one of the things that I think hasn't been mentioned a lot so far today is the history that the School of Computing has with networking. So, and the University of Utah in general has with networking. So I want to, we'll spend the next panel talking about that. And, of course, I can't go into this whole history, but we'll look at it through the contributions of a very specific research group that I co-lead, the Flux Research Group. So I'm Rob Ritchie. I'm a research faculty member here. And I co-lead the group with Eric Eide, who is here, and Kobus Vandermerwe, who maybe isn't here. And we have a couple of our alumni from the group. Both these gentlemen were undergraduates when they worked in the Flux Research Group. Both of them went on to get PhDs at MIT. Dave Anderson is now a professor at CMU, and Cody Cutler is now a software engineer at Amazon Web Services, the largest cloud company. Let's see. Okay, big green button is the next. Got it. Okay, so I have just a couple slides to introduce this thing. You actually saw this picture in Steve's talk just a moment ago. It's actually on the poster over there as well. So, one of the history of the University of Utah networking goes back to the ARPANET, which is generally considered to be the earliest direct predecessor to the internet that we have today. So actually, a few years ago, in this exact room, we had a celebration of the 50th anniversary of the ARPANET. This picture is in is the ARPANET in 1969, and it's not, it's a little bit of a hard to read picture, but you can see there that Utah was actually the first part of the ARPANET that was outside of California. So fourth node, first one outside of California. So, and none of us go back that far, right? But the point that I want to make is that this is something that Utah has always been at the center of. So where Dave and Cody and I come into the picture is with the Flux Research Group. I started here in the late 90s, Dave in the mid 90s, I guess, and Cody in like the 2010s. And this is a research group that is within the Collert School of Computing. I've got a couple of pictures up here of the members of the group through the years. These pictures are usually, I think maybe all bowling pictures. It's our annual holiday activity. But we've had something like, I looked it up the other day in preparation for this, the other day about something like 150 people have actually gone through this research group over the years. And I can't really talk about the Flux Research Group without talking about Jay LaPro. So Jay is the person who founded this group in the mid-90s. It grew out of the facilities group for what was then the Department of Computer Science. And with funding from DARPA and HP, and with the early collaboration from Bob Kessler, another giant of our department, who was around for many, many, many years. Jay founded this Flux Research Group, and many of the original members of that group are still here. Some of them are in the room with us today. And Jay led this group until he passed away from cancer in 2008, 15 years ago this year. Kind of amazing that it's been that long. But the group is still here, still working on the stuff that he started. Jay had creativity and energy that basically nobody could keep up with, and was the founder of one of the main conferences in our area, OSDI, which is has a Best Paper Award now named after him, the most fundamental thing that I take away from, my time as a student of Jay's, I think actually has come up like in a bunch of the talks today. Some of the quotes that Telly Whitney had earlier about kind of supporting people to kind of do their best work without limitations. And so Jay was somebody who was very excited by the work that he did, and was very, he deeply believed in the people that he was working with, and deeply cared about them. So, one of the great ideas that Jay had was, it's really nice actually to go after Steve for this, because Steve talked about the availability of resources. And, in operating systems and networking, it's actually really important to have access to servers that you can reprogram and break, and networks that you can reconfigure. And so the Flux Research Group had built up some infrastructure like that on its own, and the truth is that actually lots of other people need this infrastructure. And so we have, one of our major activities since then has been building test beds for the networking, operating systems, cloud computing, database systems, right? So in 1999, we started building Emulab. This was operating a multi-tenant, remotely accessible data center with reconfigurable networking and storage. And if that sounds like a cloud long before the cloud existed, that's pretty much exactly what it was. So it has gone from something that was literally assembled in the hallway of MEB. Those of you who are around at the time when the terminal hallway was in MEB, this is the terminal hallway assembly. This is the first assembly party in 1999, I believe, assembling hardware, to something that now runs in the University of Utah's state-of-the-art downtown data center as a globally accessible resource that's used by people all around the world. I just went into the Wayback Machine and took a couple of screenshots of our very Web 1.0 original web page. It's kind of evolved a bit through the years, but that original kind of vision of building something that is an infrastructure for computer science researchers has branched out into building ones for the Powder test bed, which is a wireless test bed that actually covers a large amount of this campus that we're on now. The Cloud Lab test bed, which lets experimenters come and build their own clouds, and it was a major part of GENIE, which was the National Science Foundation's worldwide programmable network test bed. So speaking of worldwide, people have been using these facilities, not just here at the University of Utah, but this is a recent map of our users, in just about every U.S. state and in a large number of countries all around the world. So with that, I'll kind of move on to, we'll leave it here, and I'll move on to talking to our panelists here. So if I could get each of you to start kind of, Dave, first maybe talking about when you joined Flux and what you were doing when you first joined.
Absolutely. It's great to be back, by the way. Thank you for inviting me. So I joined Flux in about 99-ish or so. I had previously been a very delinquent biology and computer science student here. I apologize to the biology department. I founded an internet service provider called ARPANET that some of you may have used if you were not using my much more successful competitor XMission, which was also formed by a University of Utah alumnus. But I decided I'd had enough of the real world and I wanted to come back to do academic stuff. And Jay LePro was nice enough to kind of take me under his wing and let me hang out as an undergraduate researcher and then a research associate for the year following when I graduated. What else do you want to know?
Yeah, how about you, Cody?
Let's see, so I actually started my undergrad education at UVU down in Utah Valley, obviously. And I was kind of getting bored with computer science actually at that point. And I realized that I was going to switch to the math major, but then decided that I would also attempt to go to the University of Utah instead. So I actually transferred up here and was so stunned by the quality of the first CS class I took that I decided to remain CS. And in order to fund my education, I had to also get a new job because I moved up here. And I first went to the CADE lab to continue my IT work. And turns out they weren't hiring, but they directed me to the Flux lab. And we met, and things obviously went pretty well. So I ended up working there, and started with a very interesting project that ended up turning into a paper that kind of jump-started me into heading to grad school eventually.
Excellent. So Dave, you were here when when Emulab kind of was really getting started. I actually looked up your first commit to the source tree last night.
Lord.
It was about divert sockets in FreeBSD, actually.
I love this.
So anyway, but I wonder if you can kind of tell me a little bit about kind of what problems that building, it was originally called the testbed for many years before it actually got a name, Emulab. But I wonder if you can tell us a little bit about like some of the problems that the testbed was built to solve.
Absolutely. And I'm going to complain here, which is that I apologize. It's hard following a graphics talk. I once had a DARPA program manager say to me, Dave, I don't ever want to see another ping demo in my life. And here I'm going to tell you about building ping demos. So the way this all started is we had, in the Flux group, Jay's group had assembled this test bed of machines in this back closet. And it was this under air-conditioned, overheated room of like these beige PC boxes that they would use to do all of their operating systems research. They were working under a bunch of contracts from HP on the venerable HP UX Unix system. They did some work developing successors to the Mach operating system, which you may know as the thing that actually underlies OS X. And then there was a whole bunch of follow-on work with the infamously named FL projects, which Jay's name, of course, Frank Lepro, wouldn't have anything to do with that. But it was the Flux group, the Fluke operating system, the Fluke microkernel, the Flick IDL compiler with Eric, and all of these things. But as operating systems projects, right, you have this problem. And the problem is you crash your operating system and the machine is just gone. Right? And then you have to walk back to the lab and you have to push the button. And then you walk back to your desk and then it boots and a minute later it crashes again because that's the nature of operating systems research. And so it was a really good way for people to get their exercise walking to and from this machine room, but it wasn't particularly good for productivity. And the way the Emulab actually got started was the annoyance of having to manage this cluster. So the first thing that happened before I got there was there were remote power cyclers for these machines. So you could click a button and it would, or run a command line, and it would reboot the machine. But then it would reboot the machine into possibly the same broken state that it was in when it started. And then you had to go and push some buttons again. So one of the first things that we added, and this was probably, I think this was actually my contribution, was a little kernel image that you could boot remotely that would copy a new image onto your disk. And if you were in the cloud world, you could think of this as initial provisioning of these machines. And so that operating system onto the disk loader then was one of the stepping stones we took towards this. And once we had that, we had this cluster that, hey, we can load an arbitrary image on. We can copy we liked FreeBSD and things back then. Linux, for those of you who are modern, we can copy Linux on there. We can copy whatever on there. And then networking people said, hey, well, what about using it for my network stuff? And so we added these things we called delay nodes, which were you could route through another computer and have that computer add arbitrary sets of network delay or loss. And that was this FreeBSD deferred sockets. And so it kind of built up organically from the needs of what the researchers in the operating systems and network group were doing as far as being able to test their systems in a kind of user, scientist-friendly way. And then it kind of took off.
And so to follow up a little bit on that story, so this is about when I joined the Flux Research Group. Originally we had a cluster of 40 machines that actually hosted in the same machine room at MEB that Steve Parker showed the picture of the big giant SGI machines in. We started opening it up kind of more and more to to friends and then the world kind of at large. And one of the interesting things about building infrastructure like this is that it actually like brings up research topics of its own, right? So Cody, I wonder if you would talk a little bit about the work that you did with respect to securing our bootloader.
Sure.
And yes, you can use the word toodles to refer to it. It was TDLS, and toodles is what we call it for sure.
Yes, thank you for doing that for me. I couldn't say it otherwise. So the acronym for this project that we started is TDLS, as he said. It meant the Trusted Disk Loading System. And the problem that we were attempting to solve, and eventually solving to some degree, was that if you allow arbitrary users to use these testbed nodes, and not just use them, at a high level, they actually get full access to them. They can do arbitrary things to them. If they're sneaky, they could hide perhaps code that might interfere with other people's experiments, or perhaps worse, on these nodes. And this is not a simple problem. It's not just code sitting on like a hard drive or something. It's also code that's embedded into the network card and perhaps a graphics card and elsewhere on the PC. Even the very first piece of code that runs, that actually turns out it's mutable in some cases. And so trying to make sure that all of these other potential vectors to attack somebody's experiment, make sure that it's safe and they have not modified and they're all in a good state, that was the point of this project. And it turned out, and I'm sure not by chance, there was a new piece of hardware that had just become commodity at this time, called the TPM, or the Trusted Platform Module, which turned out to be very helpful for this particular use case. So it was mainly building this thing, and an awful lot of effort was in figuring out how it actually worked, because it was kind of, as I said, it was somewhat new then. It was a commodity, but there was no useful way to program it. So we had to do a lot of reverse engineering to figure out how to actually make it work. And another interesting aspect of this project was that this TPM in the common use case, like when you use it on your laptop or on a phone, the boot order is much simpler than what we had running in Emulab on the network nodes, where we would boot to the network and then have to go through multiple other stages before we finally got to the thing that the person running the experiment wanted to actually run. I think those are the salient bits.
And actually, if I can build on that.
Yeah, please.
For some odd reason, you have a person from AWS here and a person who spent 4 years at Google here. And I can say that this problem of securely reestablishing your hardware environment is foundational to both AWS and GCP's ability to provide hardware. And Jay's group was somehow tackling it in the early 2000s before either of these things was a glimmer in their mega corporations' eyes.
That actually leads really great to the next thing I was going to ask you guys about, which is kind of to talk a bit about what you guys have each done since you left the group, and how the kinds of skills you developed here at the University of Utah have kind of been a part of that.
I'll start if you don't mind.
Go for it.
Let's see. So I actually visited the operating systems class this morning and spoke a bit about this already, so I have my answer already for you guys.
Excellent.
Let's see. So specifically from the Toodles work, that was one of the rare opportunities where you get to do a bunch of bootloader hacking, which I think opportunities to do that outside of the operating system class basically don't exist for the most part. And this knowledge would end up being super useful later in graduate school when I ended up building an operating system for my research. But then also, believe it or not, at AWS, at the service I work on, EFS, the Elastic File System, writing assembly there has also been pretty important for some performance cases. So as far as general assembly competence goes, that aspect was useful. And then, of course, I'm glazing over some other details here about other aspects of setting up the hardware in a secure way, which I probably can't talk about anyway. Let's see. And I guess after that, after my undergrad, when I did my research project for my PhD, that project, the point was mainly to show that you could build an operating system kernel that had reasonable performance in a garbage collected language, And so a lot of that work was on memory management. And again, another way that unfortunately I can't go into a whole lot of detail about, that has enabled other recent project that we are working on in the service now on the storage side.
Awesome. Go for it, Dave.
Awesome. Well, I was part of this JLAPRO to MIT pipeline that included me and Cody and Brian Ford and Austin McKinley and a whole bunch of other former ruffians from Utah. So I did my PhD on resilient networking. How can we make connections across the internet more robustly? And the weird thing was, this was a problem that I picked up at Utah. One of my collaborators lived in Corvallis, Oregon, and he had relatively crappy internet connectivity. And there were a couple times we observed that when, his name was Lee Stoller, when Lee
He's
would...
watching now, by the way, I'm sure.
Oh, Lord. Just what we need. Hi, Lee. So when we would... Lee was unable sometimes to connect from his house back to the Flux group. But I still had machines at this internet service provider that I helped create. And I would let Lee go to my machines and hop into Utah, and it would work. Which makes no sense at all, right? You're like, the network is working, everybody's internet seems happy, and yet you can't go from point A to point B. And somehow 5 years later, that turned into my PhD dissertation. So thank you, Lee, wherever you are, you inspired it all. But no, I think my following career, actually, you could copy paste half of what Steve Parker just said. So one of the first things is that I believe strongly in real working code, which is something I picked up from Jay. And the second thing is that performance per watt has come to dominate my life. And I have absolutely nothing to do with graphics. I took Pete Shirley's graphics class, and it was astounding. And I can't multiply a matrix to save my life. Which is funny, because I spent a bunch of time helping with machine learning frameworks at Google, too. But really, I can't. So I'm a systems person, but performance per watt matters everywhere. Because Dennard scaling ended, right? Dennard scaling was this thing where as we shrunk our transistors, we could reduce our voltage, which meant we could reduce our power. And when that stopped, it meant that we had to find other ways to become radically more efficient. And that's mostly been through parallelism and through, even worse, vectors, right? As a systems person, you're like, vector math, how do I use vector math to help people open their files, right? That doesn't seem like the kind of thing that we do. And so starting in about 2008 or so, when these trends became apparent, most of my research has been focused on this question. And a lot of what I've looked at is the question of memory efficiency. Because it turns out the things that eat power in a computer system are CPUs doing lots of math, and RAM consumes a fair amount, and moving data is deadly, right? Moving data from one place to another. That's why we have all these caches, we have fancy graphics RAM, because data motion is really expensive. And so a lot of what I've done, Steve Parker could also have advertised to you, because I steal ideas from my theory colleagues. I'm not a theoretician, I just poach their ideas, and I try to take them into practical systems contexts. Like, how can we build hash tables that use substantially less memory? How can we build database indices that use substantially less memory, and things like that. So the same driving factors that Steve was advertising to you all are the same driving factors that actually have been the core of my research for the last 15 years. It's really fun.
So actually, so I think another thing that I like to ask you guys to expand on a little bit is, I think we've talked a little bit about how some of the work that was done kind of early on in Flux is now just kind of what the networking world looks like, what the cloud and data center worlds look like. So I wonder if you can kind of comment on some of those things that you might have seen in your time here that just are kind of part of the way that we expect the computing world to work now.
Please go ahead.
Well, I was going to say his secure bootloader and configuration system, right? I mean, in many ways, what was happening in Flux presaged half of what you see in cloud, right? We had distributed file systems, which you had to use to access the nodes. We had secure bootloaders. We had reconfigurable networks. Like one of the examples was something that a colleague of ours named Chris Alfeld worked on. He went to get his PhD at Madison, I think?
He got his PhD in Madison in math.
In math,
yes.
yeah. So he was the opposite direction.
That's right. And then he came back to computer science and works at Google now.
Don't we all? Which was this problem of we called it the test bed assignment problem. And it was, you've got a cluster of hardware resources, and you've got a bunch of user demands, like, person A wants 5 machines connected this way, person B wants 6 machines. How do I map that into my available pool of hardware resources without stranding lots of hardware? And this is a problem that Amazon and Google and all of these other providers have to deal with daily.
And by the way, I'll mention, so Chris started that, Dave worked on it a bit, and then I got my dissertation from it. So thanks, guys.
So there you go. But actually, all of the problems that they had to deal with in some way are mirrored at radically larger scale, so the solutions differ when you go into an Amazon or a Google context. And you can probably tell more honesty about how much the solutions actually apply.
I mean, unfortunately, I really can't. Like, I would love to give a better example of how it could work, or the work that could apply at EC2, but like the Toodles is probably the only good example I can think of.
All right, excellent.
I was just thinking, have you ever thought of being on Saturday Night Live?
Dave was just asked if he would like to be on Saturday Night Live.
I'd get booed off the stage.
Let's see. So I wonder if you guys could comment on kind of the way that kind of the availability of resources to do your networking and operating system work on, how that is kind of enabling of, I don't know, the ability to do anything in systems.
Yes.
Okay.
It really is. No, to give an example, when I went to grad school, one of the things I had to do for this robust networking project was I had to have points all over the United States and the world where I could measure what was going across the internet and whether it was reliable or not. And nothing like that existed, so I had to build it. And I used a bunch of my connections from my ISP days. I was like, hey, can I send you a machine and you just put it on the network? And bizarrely enough, people said yes. And then I realized I had this test bed of like 20 machines out there that I had to maintain as a grad student. My advisor was very, very forgiving, bless his heart. And so I did what anyone would do, which was that I turned to these folks and I said, can you please help me? Let's make this a test bed that you maintain and that I can use. And they crafted, actually it was this little CD-ROM that we then mailed out to all of the hosts of this network test bed.
We even handed them out at conferences.
Right, can you just stick this in a machine and it will re-image our machine, and now it's maintained by Emulab and we can actually make everything work. And grad students today come to expect that capability, right? They're like, I need to do some networky stuff. Let me load up Emulab and pull up a dozen machines all over the world, and I'll do some file transfers and everything will just work. And it makes the lives of grad students a lot easier now, so that they can have hard things other than that to focus on.
Yeah, I was going to say, it gives them other hard problems to work on.
They can focus on the important parts.
Yeah, so I personally was not a network. I didn't do a lot of research in networking. It was mainly, like I said, on operating system kernels. However, and building a kernel doesn't necessarily require building a topology and experimenting on it. However, early on, I was doing research on performance of distributed systems, and that was probably the main way that I ended up using Emulab, despite the fact that I spent a lot of time building Toodles and other features for it before then. The main way that it helped me do research was I was actually able to run realistic performance experiments for this research project. So it enabled that. It ended up not having a great research impact, unfortunately, but that's the way cookie crumbles sometimes.
So I think maybe to get us back on time for our next keynote, I'll just ask you guys one more question. So first of all, I want to say a lot of members of the Flux Research Group are actually here in the room today. So I wonder if the staff and students could stand up really quick. Come on, looking at you guys. I see you guys. Stand up. Okay. So thank you. So to the students who are here, right? I wonder if you guys could, if you have anything you like, any recommendations to make to the people who are now at their point in their career that you were when you were here in Utah, in their research careers. Uh-oh. I'm not sure I prepared them for the fact that I was
I
gonna
was
ask
not
this.
prepared for this.
Okay,
And so
sorry.
what I can do is I can point back to Steve's list again, because
Okay,
it was actually a
excellent.
really good one, right? Which is that you need to find a supportive mentor. Jay LaPro was an amazing mentor. But so were Pete Shirley, right?
Mm-hmm.
So was John Carter, right? These people were all incredibly supportive, and right, it feels really weird to be this kid from Utah who ended up at a big name university. And I still feel like that kid from Utah, and it's thanks to Jay and John and Peter and Al Davis, with whom we co-taught each other networking for a while.
I'm surprised you stayed in networking after taking the course. I did not know how to teach.
I didn't know how to learn. But the mentor part is awesome, and finding a driving problem that really grabs you, right? I found it personally, and this may just be me, really important to find a problem that it got me, right? This problem of Lee Stoller not being able to connect to Utah. It was like, why? This is wrong. It wasn't just like wrong, it was morally wrong that the internet was not working for him. And I was willing to then dedicate the next 5 years of my life to solving it-ish. In an academic sense. And then do pay attention to these really long-term fundamental technology trends, because they are radically changing the way that research and the production actually happens, right? Performance per watt is dominating everything from a systems perspective, right? Moore's law, I call it Moore's zombie now. Moore's law is dead. It's still kind of shuffling around, right? We have a couple generations of ASML giving us, now they call it extreme ultraviolet. I call it soft X-rays to make it sound a little more scary, right? But as we can, it gets harder and harder, right? Things will get more and more expensive. So looking at those long-term technology trends so that you're not doing something that's going to be a dead end. I think if you can combine if you're lucky enough to be able to combine all of those things together, you're going to have a really fun time.
And I'll just plus one the mentor advice. Like, had I not stumbled into Flux and met Eric Eide and Mike and Rob and worked with them and the other colleagues at Flux, my life certainly would have been much different. Like, they introduced me to research and encouraged me to go to grad school and find interesting problems to work on. So it was a great impact on my life.
Excellent. Okay. Well, thank you, everybody. Thank you, sir.